To establish verifiable trust on an untrusted network, we must first strip enterprise data down to its raw, vulnerable bit stream. The central problem of modern networking is transmitting sensitive information across a global architecture where every node and physical connection is fundamentally unsecure. Modern cryptography functions as an arms race between keyspace volume and the increasing velocity of computational cryptanalysis. This chart illustrates keyspace generation. An algorithm locks plaintext using a specific sequence of random bits, drawn from an allowable range of values defined by the protocol. Adding a single bit to a key length doubles the available keyspace, creating an exponential barrier to brute force discovery. Security rests exclusively on the mathematical randomness and protection of the key, while the encryption algorithm itself remains entirely public. The historical baseline for this is the Julius Caesar substitution cipher, which secured military communications by shifting each letter of the alphabet 3 positions. Simple substitutions fail against frequency analysis. By studying the statistical distribution of letters in the ciphertext, cryptanalysis can identify repeating patterns that expose the underlying key. The speed of 20th century warfare required a mechanized defense against frequency analysis. The German Enigma machine utilized physical rotors to create constantly shifting letter substitutions, effectively changing the encryption parameters with every keystroke. In response, the Allied bomb machine industrialized cryptanalysis by mechanically cycling through thousands of rotor positions to find a valid keyspace match. Simultaneously, William Friedman dismantled the logic of the Japanese purple machine, proving that no mechanical cipher was immune to analytical breakthroughs. This algorithmic locking of data is distinct from steganography, which relies on hiding data in plain view, such as within image pixels, rather than securing it mathematically. Historical machines prove that fixed-length encryption parameters inevitably fail as the adversary's processing capacity expands. To secure massive volumes of data at rest, engineers rely on symmetric algorithms, where a single shared key performs both encryption and decryption. Symmetric systems deploy as either stream ciphers, which encrypt plaintext bit by bit, or block ciphers, which process fixed mathematical matrices, transforming 64 or 128 bits simultaneously. Block ciphers evolved from IBM's 128-bit Lucifer algorithm into the 64-bit Data Encryption Standard, or DES, adopted by the NSA. By 1998, advancing computational power rendered the 64-bit DES keyspace obsolete, allowing researchers to brute force keys in less than 3 days. The immediate patch was triple DES, which ran the DES computation 3 times with different keys to provide a temporary stopgap against exhaustion. The modern standard is the Advanced Encryption Standard, or AES, supporting keys up to 256 bits, alongside robust alternatives like IDEA, Blowfish, and RC5. Symmetric algorithms are efficient, but limited by key management. Sharing a single key across an insecure network presents a significant architectural risk. Asymmetric cryptography solves the distribution crisis by using 2 mathematically linked keys to establish trust over a public network architecture. The RSA algorithm achieves this through a one-way function based on the computational difficulty of factoring incredibly large numbers. The Diffie-Hellman protocol established a method for sharing a secret key over a public channel, though it does not provide the actual message encryption. For mobile devices with limited resources, elliptic curve cryptography provides equivalent security with much smaller keys and lower processing overhead. Similarly, the Elgamal algorithm relies on complex discrete logarithm problems to generate digital signatures and exchange keys. Modern security uses a hybrid architecture. Asymmetric math securely exchanges the key, while symmetric math uses that key to rapidly encrypt the actual payload. Encryption provides secrecy, but message integrity requires hashing to guarantee the data was not altered during transmission. Hashing algorithms convert variable-length data into fixed-length fingerprints. Legacy standards like MD5 and SHA-1 have been abandoned for secure modern digests like SHA-2 and SHA-3. This diagram shows the creation of a digital signature. A hash is calculated from the message and then encrypted with the sender's private key. The recipient calculates their own hash of the message to verify authentication and technical non-repudiation. This architecture is standard in secure email implementations like OpenPGP and SMIME, which use digital certificates to verify sender identities. Public Key Infrastructure, or PKI, is the ecosystem of protocols and policies that manages these certificates across a global network. A certification authority issues certificates binding public keys to specific identities and maintains certificate revocation lists to notify the network if a key is compromised. By binding identity to mathematical keys, PKI creates a structurally sound environment, provided the central authority remains uncompromised. Cryptoanalysts target algorithm properties through theoretical mathematical attacks, such as side-channel exploits or known plaintext analysis. Against hash-in functions, attackers attempt a birthday attack to find a collision, a scenario where two distinct inputs produce the exact same hash value. Beyond math, adversaries use network interception. In a man-in-the-middle attack, an attacker places themselves between a victim and a host to capture traffic. In an SSL/TLS downgrade attack, the attacker intercepts the initial handshake and forces a server to renegotiate the connection using a weaker, fragile cipher. Replay attacks allow an adversary to capture and resubmit legitimate authentication data to fool a system into granting access. To defeat these interception attempts, engineers use HTTP strict transport security. This browser query shows HSTS forcing an upgrade to a secure connection. HSTS provides a structural defense by mandating secure channels and disallowing site access if a certificate cannot be validated. The final vector involves extracting data at rest for offline password cracking. Attackers use dictionary files and pre-calculated rebo tables to compare millions of known words against stolen hashes, attempting to exhaust the keyspace. Automation tools like John the Ripper execute these attacks by cycling through specific word list and incremental cracking parameters. Specialized tools like Hashcat and FGDump target critical operating system files, such as the Windows SAM or Unix shadow files. Engineers neutralize pre-calculated rainbow tables by injecting random salt data into the hashing function to ensure every output is unique. This injection of random data ensures that identical passwords produce unique hash values, effectively neutralizing dictionary-based scaling. Cryptography is an endless war between protocol engineering and mathematical cryptanalysis. The moment an algorithm is standardized, the countdown to its obsolescence begins.